and I did my final project on Boston housing data. And I wanted to see what I could learn from Boston housing and how we might use this information. So the data I collected was from Kaggle. It was a totally free open source data set, and it contains 506 total observations with 14 attributes, 13 continuous, and 1 binary, and it has 0 missing values. And below you can see the attribute information in detail. So from a business perspective, why would Boston housing data or housing data in general be important? And it's because geographic and demographic data is very powerful in deciding where to operate as a new or expanding business, and clients with deeper pockets are more willing to pay for goods and services. So finding which neighborhoods, boroughs, or districts have the most disposable income will drastically increase the likelihood of revenue growth in the future. So as for my methods, I used 12 out of the 13 potential predictive variables for all my models. I standardized all 12 because they were on very different scales and they were all continuous. I also used cross-validation for my classification models to sort of ease the burden of overfitting with n folds set to 5 because this was a 20/80 split. And I also decided to omit the variable chas from potential predictors because when I was doing some exploratory analysis, some visualizations, I noticed that it didn't really have any bearing on any of the variables or any of the questions that I, sought to answer. So yeah, that's why I excluded it. Exploring the data visually a little bit, I wanted to see the primary target variable for what it really was. So as you can see to the left, there's a histogram of, the home values. And you can see that it's approximately normally distributed. It's a little bit skewed to the right, but I would say that it's, it's safe to assume that it's normally distributed. And then to the right of that, you can see a correlation matrix, and values below 0.9 and below negative 0.9 would be problematic. And fortunately for me, there weren't any that looked like they were going to cause any problems with multicollinearity. And then a few more visualizations that I did. I just wanted to see to the left here, you can see the proportion of pricey homes versus non-pricey homes. And I created this binary dummy variable by taking the median value and sort of just splitting the data. So if you were below the median, you would be a red or a cheap home. If you were above the median, you would be a pricey, expensive home. And you can see that, we won't run into any class imbalance problems because it's a pretty even split, obviously. To the right, you can see that the median value of homes increases as the number of rooms per dwelling increases, and it makes sense just because, the more square footage, the more rooms, the more expensive your house is going to be on average. And then here you can see that the per capita crime rate for cheaper homes is much higher than for expensive homes. And it makes sense because, you're talking about ghettos, poor areas, lots of crime. So I'm just sort of exploring some assumptions that one would make about housing in general. As for question 1, I wanted to see how we might go about determining whether or not a Boston home is expensive with the data that we had available. So again, to do this, I decided to turn it into a classification problem because I assumed it would be easier to predict a binary variable rather than a precise continuous number. And for this classification problem, I used logistic regression and decision tree models. So as for the logistic regression results, after running the model with k equals 5 folds, the results were pretty promising. The average accuracy score across all 5 K-fold models was 82%, the best being 90%, and the worst being 73%. And intuitively, the variable that most clearly explains variation in home price is definitely the number of rooms, as you can see on that on those exponentiated coefficients. So essentially, if your home had more rooms, you were 397% more likely to be a pricier, expensive home. And also, if you had good access to highways, you were 29% more likely to be a pricey home. And finally, the AUC for the area under the curve of the receiver operator curve for the weakest model was approximately 0.7, which is, as a rule of thumb, considered acceptable. So overall, I'm pleased with the results from the logistic regression model. For the decision tree model, the model followed the exact same process as the logistic regression model. The average across all 5 K-fold models, the average accuracy, of course, was 83.2%, which is pretty good. The area under the ROC curve for the last model was 0.85, which is substantially better than the logistic regression model. And this basically means that the model was about 35.3% better than chance, and overall, the decision tree model performed the best out of the 2 for the first question. So as for question 2, in the city of Boston, is there a higher crime rate when the median values of homes are lower? How might we go about predicting crime rate? So as you might have guessed, here I wanted to try to predict crime rate. And to do this, as it's a continuous variable, I wanted to use ridge regression and lasso because I wanted to see if they would outperform ordinary least squares. And I also wanted to see which variables were important. So both models were underfit, with the testing error being lower than the training error. The R squared for the ridge regression was worse at 0.4 versus lasso at 0.69. And since coefficients were standardized, the interpretation of the lasso coefficients, for instance, LSTAT, was increasing LSTAT, or lower status of the population, by 1 standard deviation, which was 7.14. This would increase the crime rate on average by 1.677, or the beta, the coefficient that you see there. We can also see that lasso reduced age, room, and tax to 0 because there were, greater severity on the penalty term compared to ridge regression. So these variables weren't very important, which I found pretty interesting. Overall, the best model was lasso, meaning that for the crime rate, not all variables matter a little, only a few actually matter. So as for question 3, does the number of rooms per house increase or decrease with an increase in the, and that's supposed to say pupil to teacher ratio. Again, pupil to teacher ratio. In Boston, what factors determine the pupil to teacher ratio? So here I didn't decide to predict anything. I wanted to use Gaussian mixture and k-means, unsupervised learning, to distinguish neighborhoods and select, the best area to set up shop. So as you can see, after experimenting with k a bit, I decided to go with k equals 5 for the final model. I wanted to keep the number of clusters small, and I was going for parsimony while choosing the highest silhouette score. So overall, the k-means model was all right. Interestingly, though, as you can see by looking at the graph, the clusters were just what we might have expected to see. The groups, or the clusters that are red and green with higher property values, had lower crime rates and smaller pupil to teacher ratios. This is because you would expect to see lower rates of overflowing classrooms in wealthier areas with more funding. Also, the groups with smaller pupil to teacher ratios, the red and green again, have less lower status individuals in them. As for the Gaussian mixture model, based off of the silhouette scores for each number of components, 2 through 7, the best was 7 components, which had a silhouette score of 0.5187. Again, not the best silhouette score, not the best cohesion or separation, a little bit hard to differentiate between the clusters, but you know, as always, I would have hoped for a little bit better. And interestingly, you can see that groups 5 and 6 from the Gaussian mixture model had a lot of similarities with groups 0 and 2, again, the red and the green from the k-means model, in regard to several key indicators for the pupil to teacher ratio. Finally, to conclude, you know, although the data was very clean and precise, I would have liked more features and just more than one city. So if I could, I would, you know, go back, do a few revisions, and these might be cross-validating ridge and lasso models, implementing a Burj-Pagan test for ridge and lasso to see if the model was, you know, heteroscedastic, and see if I might be able to correct that. Also, I would try running elastic net because it's sort of like a hybrid between ridge and lasso. And I might consider including the CHAS variable that I excluded, that factored variable, just to see if I can improve the predictive power a little bit, and also to see if it would have any resistance to the ridge and lasso models, if it would pop up. And I might also narrow down the data set to just the top 10% of the most expensive homes. But again, it's a really small data set with just one city. So I didn't want to, you know, only have 30 observations in my test set, or you know, 50 observations in my training set, something like that, maybe even less. So yeah. As a final recommendation for any business looking to set up in a certain area, I would set up shop in a neighborhood with good access to highways, an area with low pupil to teacher ratios, areas with high property value, less nitric oxides, less crime, and more bedrooms. So yeah, that's it. Thank you.